Good morning. So this is lecture about our sun. So basically in this lecture we'll study the internal structure of our sun, its composition, and how the sun emits energy which we receive in the form of heat and light. So let's get started. Our goal for learning will be why was the sun energy source a major mystery? Why does the sun shine, and what is the sun structures? So we'll try to answer these three questions. So the first thing you need to know is some information. So the radius of the sun, which is from the center all the way to the edge, is about like 6.9 to the power 8 meter. Okay, so it's like 109 times the Earth radius. The mass of the sun is like 300,000 times greater than the Earth mass, which is 2 into 10 power 30 kilogram. And the luminosity, which is kind of brightness, is about 3.8 to the power 10 to the power 26 watt. Now remember, the light bulb that we use at our home is about 100 watt, right? And so 100 watt light is so bright. So just imagine how bright it's gonna be, especially for the sun, which is equivalent to 3.8 into 10 to the power 26 watt. So why was the sun energy source major mystery? So first question we're going to answer. So first, in ancient time, they thought that might be, is it on fire? That the sun is some sorts of fire. But the answer was no, it can't be, because the energy needed, and if you see the brightness, so when you compare the energy and the brightness, then this fire source could only last for like 10,000 years. So then, is it contracting? So then other, reason that was given for the sun energy was like the sun is contracting, so they are releasing some kind of energy. Now again, if it's contracting because of gravitational potential energy, and then when you compare that energy with the luminosity, which is brightness, then it only gonna last for like 25 million years. But as we know that our sun age is already like 4.6 billion years, so this hypothesis cannot be true. So this is also no. And then finally it came that might be it is powered by some kind of nuclear energy. Now remember, E is mc squared given by Einstein. So yes, when you compare its nuclear energy and then compare with the brightness, then it's about like 10 billion years. And this hypothesis was correct. So that means our sun is going some kind of nuclear fusion reactions that produce energy by fusing like 4 hydrogen into helium. I'm pretty sure you remember that one, right? Okay, so the formation of sun, we already talked about this. They are formed from a giant rotating cloud of gas and dust known as solar nebula, right? So nebula is a cloud of gas and dust. So when they contract, they produce heat energy. And when the temperature of, at the center reaches like 100 million degrees Celsius, they, start to cook hydrogen into helium, which is also called a nuclear fusion reaction, and that was the formation of the sun. So this gravitational contraction provide the energy that heated the core as the sun was forming. So at 10 million Kelvin, hydrogen start to fuse. So basically it's a 10 million Kelvin, but on average it's like 100 million Kelvin. But this is the minimum temperature required to start any kind of nuclear fusion. So when they fuse, they produce a tremendous amount of energy, right? And then what's going to happen is sun is producing energy, so that is pushing this gas and dust outside, and gravity is trying to collapse. So green line represents the force of gravity, red line represents the energy that released from nuclear fusion. So when these energies are equal and opposite, the balance, which is an equilibrium condition, and the sun size is constant. So that means it does not increase or decrease. So what I'm trying to say is the pressure from the gravity, right, and the pressure from the nuclear fusion energy, they are equal and opposite. So I just put that nuclear supplied by fusion maintains the pressure that balances the inward cross of gravity, and that is the reason our sun is kind of fixed size. So nuclear fusion, again, is the same thing. Please go through this slide, and then hopefully you'll understand that the 4 hydrogen, when they combine, they produce, so 4 hydrogen, when they combine, they produce a helium and release a tremendous amount of energy. And if you see the age of our sun, so the sun is already been like 4.5 billion years old, and the total age is like 10 billion, so it's almost in half of its lifetime. Okay, then we'll see what is sun. So now we'll change our definition slightly. Okay, so initially we saw that sun is simply made of gas and dust particles, and then heated by a contraction. But now our definition for the sun gonna be, sun is made up of ionized gas. So it's not simply a gas, but it's an ionized gas known as plasma. So I want you to remember the word plasma. Okay, so again, what is plasma? So if you heat any kind of gas to a high temperature, that gas will lose some electron, right? And when they lose some electron, they whatever the left is termed as ionized. So basically any heated gas is termed in terms of ionization is called plasma. So basically the sun is made up of plasma. No sharp boundaries exist between its various layers. So that means we don't have very sharp boundaries. Keeping this in mind, we divide the sun into 4 basic parts. Okay, the solar interior, so anything that's inside the sun. Photosphere, so basically photosphere is the outer layer. So especially when you see a sun with your naked eyes, whatever we see is a photosphere. So it's kind of visible sphere. Then comes the chromosphere, and then finally it's called corona. So we'll talk this in more detail. Okay, so this is the core. So when we talk about the solar interior, inside the sun, we divide the sun into 3 basic regions: core, radiation zone, and convection zone. It's same like Earth, we divide into crust, mantle, and core. For the sun, we divide into core, radiation zone, and convection zone. So core is basically this internal part. So energy is generated from this core, of course, because of nuclear fusion. And remember, the temperature is about like 15 million Kelvin inside the sun. The radiation zone is somewhere in between. So this is your radiation zone. For the radiation zone, simply it's called radiation because the energy is emitted through this zone. Okay, so that's why energy is transported upward in the terms of photon. Now, if you remember, photon is when a light behave like a particle, so we call photon. So those particles are radiated from this layer. That's why we say it is a radiation zone. And then comes the convection zone. So convection is when energy is transported upward direction. So this is your convection zone. All right. Then comes the photosphere. So again, the photosphere is the region of the sun that radiates energy to space, which is the outermost layer. So basically, if you see, this is the photosphere right here in this diagram. And this layer is only visible layer. So again, it exhibits a grainy texture. So if you are wondering how it's going to look in low brightness, so it's like grain structures. It consists of a layer of incandescent gas of about like 500 kilometers thick. So that means if you see this layer, although in this diagram it's a very thin layer right here, but the thickness of this is about like 500, which is almost like 300 miles thicker. So most of the element found on the earth also occurs in the sun. So basically this is the area or region where most of the elements are formed. And again, the temperature of this outer surface is about 6,000 Kelvin. Okay, so that's the temperature of the photosphere. Now remember, the inside the sun, the temperature is very high. It's in million Kelvin, right? But if you are comparing the temperature, on the surface, it's only like 6,000 Kelvin, which is more like effective temperature of the sun. Then comes the chromosphere. So chromosphere is, is like this layer right here in this diagram. If you see, this is spikes right here. This spike is chromosphere. So chromosphere is the first layer of the solar atmosphere, found directly above the photosphere. Again, so this was photosphere, and now this spike, right, the specule structure, this represents the chromosphere. Again, it behaved like atmosphere of the sun. The temperature is about like 6,000 to 20,000 Kelvin, and this might extend to like few thousand kilometer. Okay, and then it top contains numerous spicules, which are like narrow jets of rising materials. So it's kind of like some kind of material, like ionized materials. They are like trying to eject from the surface and making these spikes. So these are called chromosphere, and again, it is not visible from our naked eyes. We cannot see these chromosphere with our naked eyes. Then comes the corona. So corona is the outer layer. So if you see, so this was your photosphere, this was your chromosphere, and if you see anything beyond this region, so this all outer area, this reddish area is termed as corona. So again, corona is the outer layer of the sun. It's a weak layer of the solar atmosphere, and the temperature of this corona is about 1 million. I mean, it's more than 1 million Kelvin. Scientists are still wondering to find how or what causes the temperature to be 1 million, beyond the sun surface. So again, inside it's like 14 million Kelvin. The photosphere has like only 6,000 Kelvin, but if you see the corona, is more than 1 million Kelvin. Again, chromosphere and corona are not visible through your naked eyes, but these two spheres can be visible at only at a time, especially during total solar eclipse. So when you have a total solar eclipse, this is the picture you're going to see with your naked eyes, right? So these yellowish spikes, these are called chromosphere, and this reddish area is called corona. Okay, so just remember, you can only view this chromosphere and corona during the full solar eclipse, right? And again, the chromosphere is the small spikes, whereas the corona is the outer layer, which is the more like reddish layer of the sun. So then comes the structure of the sun. So basically, when we talk about the structure, we also talk about the solar wind. So solar wind is a stream of proton and electron ejected at a high speed from the solar corona, and it's simply when magnetic pole of this sun, they shifted, or when they shift from one pole to the other pole, some kind of stream of proton and electron is ejected from the surface, and that is coming out in terms of what we call solar wind. So if you see this picture, nothing is there in the first picture. Second picture, you can see small jets ejecting from the surface right here, and then it leave the sun surface and they travel in the atmosphere. Now this solar wind, when they travel, they might encounter the Earth's surface. And if we don't remember, the Earth has magnetic field that is protecting us from this solar wind. So if Earth does not have this magnetic field, we might, all the life, the entire Earth will be destructed by this solar wind. So our Earth magnetic field is again protecting us from this solar wind. And then comes the sunspot. So sunspot is a dark spot that we can see in the sun. Basically, there is no such thing called dark spot, but this spot appears just because of the difference in the temperature. So when you see the sun surface, the temperature is like, let's say, if the temperature of the surface is like 6,000, and these appear darker because the temperature at this point is less in compared to the other part. So remember, when you have a two different temperature object, one will appear like reddish hot, one will appear like dark in color, right? So again, the sunspot is just because of the difference in the temperature. So basically, what we have learned, please go through this slide. So why was the sun energy major source mystery, and why does the sun shine? So basically, I gave you a very short review. I mean, this might help you, when you read these lectures. Now, if you have any questions or concern, just let me know. Just shoot me an email, and then if you want to talk me live, I can send you a Zoom link, and then we can talk in more detail. All right. Thank you, and I'll see you in next lecture.